This figure compares different parameters for cooling magma ocean planets that are dominated by the different volatile species that are shown here. The pressures and therefore the total budgets of these volatiles are normalized to create an atmosphere of 260 bar surface pressure after solidification to be able to compare the radiative properties and feedback effects between solubility, outgassing, and radiation. Now, figure A shows the net heat flux to space, which I've explained in an earlier figure. Figures B and C show the surface temperature of the planet at the interface between the mantle and the atmosphere. Figure C shows the mantle melt fraction, meaning how much of the rocky mantle, the silicates, is actually in a molten or in a solidified state. D, E, and F are related to the availability of the specific species in either the mantle or the atmosphere. Let us zoom in a bit into B and C, which are the most central here. This is surface temperature and this is mantle melt fraction. And it's plotted in time, in log units of time in years. Now what you see is that there are three principal classes of magma ocean cool down behavior. One, which is composed of the ones for N2, CO, and O2, which show a relatively fast cool down behavior. A middle class, a second class, that is composed of the H2O, CO2, and CH4 cases, and one that is composed only of the H2 component or the H2 dominated planets, which show a very protracted solidification timescale. Now, the properties of these classes can be explained by the feedback between the solubility in the magma and the radiative properties of the specific compounds as greenhouse gases.